Ben is going to kick us off today, but I want to give a brief overview of the program for the day. So the end goal today is to give you an introduction to a burgeoning area of research on loss functions for imprecise probabilities, in particular for sets of almost desirable gambles. So we're going to start the day. Ben is going to give us a brief tour through the history of scoring rules, loss functions for precise probabilities. And then in the second session, I'm going to take some of those ideas and see how they might extend to sets of desirable gambles. We're going to lay out the theory of loss functions for sets of desirable gambles. Come on in, Thomas. And then in the final session, I'm going to show you one potentially useful application of these, namely in neural net classification. We're going to walk through, those of you that have done the Anaconda installation, you have Python, you have PyTorch and TorchQuad. We're going to walk through the construction of a very, very simple kind of neural net, but see that we can train neural net classifiers with IP scoring rules, these loss functions, to learn sets of desirable gambles rather than precise classification probabilities. So that's the kind of overview for the day. Now I will hand it off to Ben. Oh, is this? I think so. I wasn't using it. I don't know if it's. Let's see. That works. The mouse works. I mean, I can just use the mouse if there should be. Maybe we'll use the mouse for now. Okay. All right. Well, the only person not thanked that really should be was Jason. So can we also give Jason a round of applause? All right, so as Jason said, we're gonna start with talking about scoring rules in the precise context. And there are a lot of different ways to think about them. So we're not gonna talk about most of that, but just to kind of preview. One thing they've been used for is maybe I'll say it a little more evocatively here. You can use them maybe to mind read, at least in theory. You want to know what someone's beliefs are. You could use scoring rules to incentivize the person, in the precise context at least, to tell you what her credences are. And with that, you can also use them to evaluate the quality of forecasts. So they'll give a score to either a single probability or expectation, or a whole bunch of them, and you can have a way of saying, like, well, once we actually learned what happened, what the value was of these quantities and so on, how well did you do versus someone else? This obviously might matter in context, like if you have a weather forecasters, you want to know who's the better weather forecaster. You might also want to, if you have, say, a betting market, you might want to see how well the market has done at predicting events. Some of these are going to kind of go together. They're basically saying the same thing. Generalized loss functions. Maybe I'll say more about that in a minute. Generalized information measures. So you can use a logarithmic scoring rule and basically get the standard Shannon entropy. But we'll see at the end of this first session, perhaps, just kind of how you might think about them as a more general measure of entropy. And then the way I'm really going to be thinking about it today, as we'll see, is as the expected disutility of your own forecasts. So you're thinking, maybe just kind of to get right in the swing of the method we'll use today. Look, I have a bunch of credences, not all philosophers here. I have a bunch of subjective probabilities. I'm going to use them when I'm making decisions. I don't really know what decisions I'm going to have to make today, right? Like I had to decide, we'll hear this maybe tired example that we'll be going back to, like, do I pack an umbrella with me today? You know, there are all sorts of decisions, what I'm going to have for lunch, all this sort of stuff. And sometimes I'm going to make a bad call. Sometimes I might make the right call, I might make the right decision, sometimes make the wrong decision. And the way that I like to think about what's the scoring rules, at least in today's context, is, well, how badly do I think I'll do with the credences I have, with the subjective probabilities I have? So I'm going to slip into philosopher talk probably a lot today. So what I like today about the method we'll talk about today, done by Teddy's illustrious colleague, Mark Shervish, is that you can make your own scoring rules with the Shervish method. But I think you'll get a kind of a deeper insight into not just being able to make one that would suit you, but to understand what they're really doing, how they're useful, how you might pick one, and so on. All right, so I'll say a little bit about kind of how they've been used. I mean, they're used in a lot of different contexts. In the philosophy context, well, I don't want to say starting necessarily with Jim Joyce, but really kind of taking off on a program, a lot of it executed here at Bristol, is thinking about scoring rules as measuring your accuracy, the accuracy of a forecast, right? So the idea, the higher credence, the higher your probabilities are in true things, the lower your probabilities are in false things, the more accurate you are, or the less inaccurate you are. And so today, well, in the philosophy context, if you like, you can think about these maybe as purely elite things. So they aren't really practical, right? It's just your purely epistemic utility. You think, well, what am I trying to do when I'm forming credences and forming subjective probabilities, or making forecasts about the quantity, some random variable? Well, what you might think is, well, I want it because I want to like get fame, I want to get money, I want like these practical goods. But the sort of way that they've been used in philosophy is that we have divorced ourselves from the world, and you can evaluate them in a purely epistemic term, how accurate they are. I think there's some problems with that. I also kind of, I don't unambiguously or unambivalently dislike it. We're going to go a very different direction and think about them in very practical terms today. All right. I probably should have made this so it's not infinity everywhere, but basically here's what we're going to do. We're going to focus on these local scoring rules, and I'm only really going to be worried partly for simplicity. There are also a bunch of complications. Teddy's done some really good work on thinking about them. Teddy with Shervish and Cadane have done some good work on thinking about it with quantities more generally. I'm only thinking about the propositional context or events, right? And as much as possible, they're not totally thinking about it for a single event. Will it rain today? You form a subjective probability. How do we evaluate that subjective probability? And so start by thinking of a local scoring rule. So it's going to score just these binary variables taking values 0 or 1. That's the second argument for G. You have some subjective probability between 0 and 1, and you get a score somewhere between, we'll just keep it positive 0 and the positive infinity. And right, let's just rule out the one that's always infinity. But other than that, I'm just going to say, weakly monotonic, it's increasing or decreasing, not even strictly at this point. So here are some examples. Right. You can take absolute divergence. So you look at, say, I being how you think of it, what actually happened? Was it a 1 or a 0? What did you actually forecast? And you take the difference. You can think of the Breyer score. as the squared divergence. A logarithmic score, I'm just doing the local one. So think about taking the negative log of your credence in the actual true event. And the spherical score, the spherical score always comes up. I don't know if people really use it too much in practice. I should have refreshed my memory on why. I think it's you project it onto a sphere and something like that. I don't know. You can look it up. So here are some scoring rules. You might also, as I was alluding to, want to think about how inaccurate a bunch of forecasts are, right? You forecast rain every day. For a year, we want to see how you did. One method you can use is just take the local rule, right, for each one and add it up. But kind of more generally, really all you want is this kind of accuracy style approach that when you're closer to the truth, you do better. So let's take this weak truth directedness. So I have a bunch of probability functions, and I'm going to give, say omega as an atom, with omega x just being the characteristic function, that world. And so if, say, the absolute divergence between p of x and omega, whether x is the truth value of x at omega is always lower than the divergence between p prime and the truth value for every proposition under consideration, then p shouldn't do worse than p prime. So any confusion? Are we kind of all together so far? So here are just some additive ones. Take the absolute one, where you just add up the absolute divergences, like you think of the taxicab distance between your credences and the truth. You can take the Euclidean distance, or you could take, the square of the Euclidean distance, the Breyer square. Okay, so one thing we're really going to focus on today is called propriety. And the big value of propriety, well, what propriety is that each proper scoring rule, each probability function in expectation assigns itself the best score. Right. So in this case, we're doing, lower scores are better. So the expected value P assigns to itself is always, well, let's say, we say for a merely proper rule, it doesn't assign any other alternative probability function a strictly lower score. Right. And a strictly proper scoring rule is one that uniquely assigns itself the lowest expected score of all probability functions. So you can see why this was really, in some practical context, maybe some epistemic context as well, a very important property. So it's going to be, I think, interesting when we get to the imprecise credences how this will work out. There are a lot of kind of impossibility theorems. Jason has a really interesting construction, we'll see. But the idea is look, if I want you to, well, I have a slide on this lower, but right, if I want you, I'm going to pay you based on a strictly proper scoring rule, or I'm going to charge you based on it, and then you'll give if you're an expected utility maximizer, and I found something linear, blah, 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 you'll give me your true beliefs, what you really believe. You'll tell me your true forecast, because you don't expect any other forecast to make you more money. And then if you're a philosopher and you care about like purely alethic goods, right? You think really what you're trying to do is just don't worry about decision making, just think about what you're trying to do when you form subjective beliefs. You're trying to believe truths, disbelieve falsehoods. That's kind of what the game is about. Then if you think of it as your scoring rule as measuring your epistemic utility, right? It would be bad if, say, when I had a certain probability assignment, that's where I really believed, my own light, some other probability assignment looks better. Like it'll get me more utility. And at least an expectation. And in that case, right, I would have epistemic reason to switch over. Oh, sorry, I should have done. Notation isn't always consistent. So a scoring rule I is proper if for any probability functions, right, it assigns itself a lower expected score than it assigns to anything else, right? So merely proper, it just doesn't have to be strict. Strictly proper, right? It's uniquely best by its own lights. Questions so far? Yeah. That's the expected value by the lights of probability function P. Sorry, I should have changed these from PRs to P's up here. So say P is a proper score, P is a probability function. The expectation function that it generates, right? It assigns itself a lower score than it assigns to any alternative probability P prime. The expected value of the score according to P. Sorry, I should have cleaned these slides a little better. I found I have like a really good general excuse for anything right now, even when it doesn't really apply, just having a newborn. So like, there'd be a lot more like images and prettified slides, but I got a newborn. If I say anything wrong, I would have caught it. If anyone wants to like ask me to referee anything, yeah. And the lower the value, the better, right? The lower the value, the better, yeah. Yeah, I mean, if you want higher value, put minus signs in front of every score. All right, so maybe just focus on, so the Breyer score is strictly proper. Don't worry about the summation, these are just additive, so just think about it like this, right? I is 1 or 0, you take your credence, your subjective probability for a single event, let's say, and it'll assign itself uniquely lowest value. But the absolute value score is not strictly proper. Here, had some don't necessarily dot all the I's, cross all the T's on this, but maybe at least convince yourself that it take a minute as an exercise. Just, don't worry about the additions, so just look at the local scores, the local value version of the scoring rule, and just take a minute to maybe convince yourself that these are that the Breyer score is strictly proper, but the absolute value score is not strictly proper. Oh, nice. Give that one slide. Oops. All right. So I mean, I think the kind of easiest way just to quickly convince yourself, right, is just so we only have one event. So if I'm evaluating an alternative forecast with the Byers score, so let's say maybe we'll quickly just work through an example, right? So I have a credence 0.6 that it'll rain. I'm thinking, how good, what is the expected value of a score that assigns, say, 0.7 to rain? Well, I think, look, by my lights, there's a 60% chance that it rains, in which case, the alternative forecaster will get a score of 1 minus 0.7 squared, right? So set 0.09. And there's a 40% chance by my lights, or subjective belief, that this person will get a score of 0.7 minus 0 squared, 0.49. Right. And I don't know, probably should have canned this example, right? But that's, you can plug that in and you'll see, I would hope, unless I really screwed something up, that that's worse than if what I would get by my own lights in expectation, right? So I think there's a 60% chance that I'll get a score of 1 minus 0.6 squared, right? So what's that? That's 0.16, and a 40% chance that I'll get a score of 0.6 squared, 0.36. And you'll see that's, yeah.
So in the formula for the inaccuracy, you are summing about overall proposition. The F.
Oh yeah, sorry, I'm trying to say, yeah, I mean, since you're going to take the score, take the sum, I mean, you can do it for all propositions if you want pretty easily because it's additive, right? So the score is always for your local score is just going to be the expectation of the sum is going to be the sum of the expectations. I was trying to say here, just worry about the single proposition.
Yeah, case. And take it out algebras for elements and for the bottom and top element.
Then you get you're sure to get a score of 0. Yeah, I was just thinking. Yeah. Yeah. Sorry. Is that?
So this is what you are. I mean,
I'm just taking an example before I do the more general.
Yeah. Well, yeah, I don't know. I'm not. Usually, you would have to do some of our. Otherwise, I'm not.
You're doing it for a single proposition in the sense that, well, it's really a pair of propositions, the proposition and its negation.
Yeah, I mean, if you wanted to prove it for the whole thing, the Bryer score is going to be proper, right? Well, what's the expected value of the Bryer score? Is just the sum of these. So if you diverge, yeah, it's slightly more complicated, but the idea is anywhere where you diverge, you're going to get.
I see, because you can swap the expectation, you can swap the two sides.
Right, you can bring out the sum. Yeah. So yeah, that's what I was saying. Let's just focus on the individual case, right? So more generally, what's the expected score? So you assign credence subjective probability X that a forecast, perhaps the same forecast, will get a score of 1 minus y squared. right? Someone announces a forecast of Y, you think, well, to degree X, I believe she'll get a score of 1 minus Y squared. And to degree 1 minus X, I believe she'll get a score of Y squared. And if you want, I mean, kind of the way to, you got to do all the stuff to make sure this is right, but the easiest way to just kind of see this has got to work out is just take the derivative. There's only, here one value, we're fixing X, right? And you'll see this is going to be 0. The derivative will be 0 when Y equals X and nowhere else. Should I do that? Okay. All right. So that won't work when it's the absolute value score, right? With the absolute value score, the expected value is X. That the score will be 1 minus Y. I guess I don't need the bars here. Plus 1 minus X times Y. So to see it's not strictly proper, you can see that it's not actually even merely proper, but just say, let X be say 0.5 and Y be, let's say either 0.5 or 1. So when it's 1, I say, well, there's a 50% chance you'll get a perfect score and a 50% chance you'll be off by 1. So that's 0.5. And when Y is 0.5, there's a 50% chance of 0.5 and a 50% chance of 0.5. So I think that also works out to 0.5. I probably, you can play with other numbers and see that it's not even going to be merely a product.
Like if you do like 0.6, you'll want to be 1.
Yeah, right. If you do 0.6, yeah, that's right. That's work out. 0.6 would be, you'll think 1 is better, right? So you'll have, let's do it that way, because mere propriety is going to come up. Sorry, I have a new one. So you have let's say if your real belief is 0.6, then and you were evaluating someone who gave a forecast of 1, there'd be a 60% chance of 0 and a 40% chance of a score of 1, which I think works out to 0.4 expected score. Whereas evaluating yourself, there's a 60% chance of 0.4 plus a 40% chance of 0.6, which is 0.48, right? So even the expectation, I did that right. An expectation, you assign yourself a worse absolute value expected score. So, I mean, there's, in some sense, especially if you're philosophically minded in the way of, well, I don't want to say just philosophically minded. If you're attracted to the philosophical picture here that a lot of people have been pushing, right? Which I don't know, this is like probably, I got to read the room, but the SIPTA crowd might not be the ones who are attracted to this kind of thing, but imagine this alternative tribe that was that liked this very like purely epistemic approach. There's kind of a little bit of a puzzle here when you're thinking, well, these are measuring how good your forecast is, but we need them to be proper. You have the absolute value score won't work as a measure of epistemic utility, purely epistemic utility. Why not? I mean, it seems like a very good, in some ways, like, maybe, some sense the first one you think of, right? I mean, it just takes, you say higher credence in truths, lower credence in falsehoods. Let's just see how far apart you are from the truth. In absolute terms, it won't work, right? So we'll kind of see what is it about the absolute, both, for today, we'll be more focused on for deeper reasons, like what are the deeper reasons why things like the absolute value score aren't going to pan out as proper? what is it that's going to distinguish them ultimately from things like the prior score? Oh, yeah.
I don't understand why the scoring takes two parameters. I don't understand what is the same. I'm scoring one subjective probability.
Oh, yeah. So you're scoring the subjective probability versus like a truth value, right? Or what actually happened. So the thing about like in the, if at that atom or whatever, the proposition turned out to be true, you get one score for your probability. Like if I forecast say a 70% chance of rain and it rains, I'm going to get a different score than when it's like forecast a 70% chance of rain and it doesn't rain.
So you're in the second quadrant, you plug what actually happened and you
Yeah, for your actual score. And then for the expected score, obviously you have to be like, well, you might get that score, you might get that score, and then weight them by your probabilities. Are we all? Okay. Oh, yeah. The Euclidean score, oddly, is not proper, is actually improper. Yeah, but if you square it to the prior score, it's proper. That's a little, I mean, harder to work with than the absolute value score, you know, but yeah, you can convince yourself of that as well. Yeah.
Is there an intuitive explanation of why squaring?
But what scoring makes it?
Squaring makes a difference.
I think the construction that we'll do in a later should at least help with one way of saying why.
Basically, it changes the derivative.
It changes the derivative. That's the easiest way. Yeah, we'll look more directly at the derivatives of scoring rules, and that'll and like, you know, why it'll be. Yeah. All right. Anything else? Right. So I think, you know, if you're into the philosophical program, the idea is you kind of want to get things like there's the probably already said too much about the philosophy, but philosophical program. But the idea is, look, we want to justify various epistemic norms. We want to say, like, you know, people like statisticians are generally going, not always, but for the most part, going to be pretty happy coming in and saying, look, we're just going to assume everything is probabilistic, right? All forecasts are probabilities, at least in a lot of contexts. And, you know, conditionalization is the best way to revise your probabilities, whatever. Philosophers, I mean, in many contexts would be happy with that, but they want sort of deeper justifications, or they're interested in justifications for why your forecasts should obey the, you know, Kolmogorov axioms. They want justifications for why you should revise your forecasts by conditioning, and, you know, other norms like that. And so, you know, traditionally, the way this worked was, you know, Ramsey and De Finetti, as we heard, right, had all these Dutch book style arguments where they said, you know, you were subject to something like a sure loss if you violated them. And that was cool. I mean, that was very interesting, but you know, some people felt this sort of violated their sensibilities. I mean, there are other problems as well with the arguments, but the idea being this is about decision making. It's not about, you know, really what should be in your head if you're kind of playing this game of just, I want to know about the world. And so you can't just say, well, I'm going to assume propriety if you're kind of in that context. But the idea would be, I'm going to have a reason why your epistemic utility, the way, you know, your true epistemic value of forecasts, I'm going to have something based on proximity to truth or something like that. And from that, I'm going to say, if that's how you care about truth, I'm going to have something akin to a Dutch book argument. Anything that doesn't obey the rules of probability is going to do, is dominated, right? It will get a strictly worse score than forecasts that do obey the laws of probability. So you can't really just help yourself to propriety, right? Like here in this mindset, some of the absolute value score, at least prima facie, looks kind of good. It assigns higher scores, or better, lower scores, I guess, better scores to truth, when you are, it's truth directed, right? Strictly better scores when the forecasts are closer to the truth. Right, the higher your forecasts are in truths, the lower they are in falsehoods, the better your absolute value score is. So like what, but if you have something like the absolute value score, the dominance argument for something like the probability axioms won't work. I'm going to try to make this the last thing I really say about that today, because we're just going to kind of put that to one side and go to an entirely pragmatic style approach to look at what is it that distinguishes these. But before we do that, right, just kind of quick review ahead, more properties first, right? So the Breyer score was so named. I mean, I think Teddy can probably tell you more about all the historical context. In the monthly weather review in like 1952, I think, so around then, Glenn Breyer came up with the Breyer score. And the real idea was, how do you get like weather forecasters to tell you what they really think, what their like true probability for rain is, right? You think there's sometimes incentives to lie, because if, right, I mean, look, if you're a weather forecaster or anything like this, I say it's gonna rain, or there's a high chance of rain and it doesn't rain, nobody's mad, or people aren't happy. If I say it's gonna rain, it's not gonna rain, and it does rain, people get a lot more upset with me. So how do you get them, so you're kind of incentivized, if you're a weather forecaster, to have a wet bias. You're going to say there's a higher probability of rain than you really think there is. So what was Breyer's idea? Well, you take a base salary, and then you deduct the Breyer score from their pay, right? And the idea being, if they're really money motivated, and and money is linear, and utility, blah 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 blah, that'll give them a reason, because by propriety, they will minimize their own expected Breyer scores if they report the truth, right? So the deduction in expectation will be the smallest from their paycheck if they report what they really think. At Carnegie Mellon, there was a professor who was teaching recently, who was using a proper scoring rule on multiple choice exams. So the idea was, instead of just saying, is it A, B, C, D, or E, you announced a forecast over, how confident you were in each, and your score on the exam was based on, how that happened, right? So you didn't just take a guess. If you were 50-50, you're best off saying, I don't know, it's between A and C. Another thing to keep in mind, and this will come out, is sort of interesting, right? It's not always the case that you can say, especially when you when you're doing a single event, it's very easy to tell who was better once you know the outcome, right? Because, if I say 0.6 and you say 0.7 and it really does rain, you were better. If I say 0.6 and you say 0.7 and it doesn't rain, I was better. Right? There's not like any ambiguity there. But when you have multiple forecasts, forecast over a bunch of events, then it's going to generally be, there's not always going to be a clear and unambiguous answer. We'll look a little bit more at this if we have time towards the end of this first session. But say there's an urn, either A, B, C, or D will be picked. Here are Alice and Bob's forecasts. And let's say, A is chosen. Alice gives a lower score to the true thing, right? A is chosen. But Bob, say, is, he's really confident in D. He has like a very peaked distribution on a false thing. So who's better? I don't know, right? There's not really like a totally unambiguous answer to who gave a better forecast over this. And if you look at the log score, you look at the Breyer score, they're going to disagree on this. Other times, right, there can't be disagreement. Like if Carol was sure A would occur and it did, every scoring rule will have to agree that she did. Okay. All right. So for the, I guess, main event, we'll talk about the service construction. I guess maybe I should speed it a little bit. So you'll see from this, why proper scoring, what makes them special, and how you get strictly proper rules when you would get those. I'm going to do this in a relatively, some parts will be kind of like, I think, relatively gentle. I'm not going to worry too much about the fine points of Lebesgue integration, but because I'm just a philosopher anyway. I want to kind of get you into the intuition behind this, and I think it'll be enough to see how Servish is going to make these scoring rules. So the way I think is natural to think about this, and I got this from, I should say this is from a general method for comparing probability forecasters by Mark Servish in 1989. It's a really good paper. I found it to be a pretty tricky paper. I spent a lot of time with this paper, but you should definitely read it. There's a lot more than I'm going to talk about today. But I think the natural way on this construction to think about scoring rules is in this expected disutility way. So it was just that when I give a forecast of X in rain, I'm X% confident in rain, something like that. I might have to make some decisions based on that'll turn on my confidence in rain. And you think more generally, again, I won't really talk about this at all. If I'm say, if I assign the expected number of centimeters of rain today to be 1.2, there might be something that turns on that. We aren't going to do the kind of more general case. But because I'm not certain of rain, right? If I was certain of rain, I would be certain I was always going to make the right decision no matter what turned on it. But because I'm not certain, I might make the wrong call. And so you can think about these scoring rules as generalized loss functions. How likely is it, or like how much am I expected to lose? Am I expecting myself to lose based on the potential that later on I'll make the wrong decision based on my creed? So it's a way of assigning yourself or other forecasters the expected disutility for having the beliefs they do. So you could think about it if I said, what about someone else, right? That would be the expected loss I'd get if I kept my preferences the same, kept my utilities the same, how much what I care about the same, but I set my preferences, I set my beliefs to something else. Or alternatively, I let someone else with different beliefs decide on my behalf, right? And gave that person power of attorney over my decisions. All right, so let's, yeah.
So you take your preferences to represent this variability?
Just utility, yeah. So think about them as, some sort of cardinal preferences over maybe the true outcome space, right?
Your probability doesn't make any, don't have any role in your preference.
I mean, they will over like the gambles over them, right? But I'm thinking the pure outcome space, keep those the same. And then, yeah. I mean, you probably have to do some work to make this fully rigorous, but the idea kind of being like, the ultimate states of the world I care about in the same way as I always did. I changed my beliefs, maybe in a good way, maybe in a bad way. How much better or worse do I expect I'd be keeping that fixed? I mean, so let's just start with a single style decision, right? Very appropriate for Bristol. So Alice is deciding whether to bring an umbrella. If it rains, it's better to have it. If it's dry, it's better to leave it at home. And assume she's an expected utility maximizer. So here's, we'll take her payoff matrix and then we're just going to massage it a bit. So if it rains, look, I mean, no matter what, it kind of is unpleasant that it rained, right? So that's not fun. You can't do anything about it. But it's, so let's say you bring an umbrella and it rains, that's the thing to do when it rains. But, you're already down a util or $1 because it rained, which is unfortunate. If you bring an umbrella and it doesn't rain, then you're worse off. You have to lug the umbrella around and all that. And anyway, tell whatever your story you like, however you like. If you no umbrella and it does rain, that's really bad. And no umbrella and it doesn't rain, that's great. So what will, if you look at this and you kind of work out the math, I don't want to go through all the algebra. When will Alice decide to bring the umbrella? Well, say, she'll decide to bring it. I mean, she'll be indifferent into bringing the umbrella if you use that payoff matrix. Make your own payoff matrix, you can work it out. She'll be indifferent to bringing it when she's 40% sure of rain. And so all that matters to how well she ends up being, right? Like what her payoff is in terms of what's under her control is whether it rains and whether her forecast for rain is above 40%. So note here, right? If you're thinking about this, from her point of view, say her forecast is 50% now. It doesn't really matter to her if she let someone else whose forecast was, say, 90% make this decision, right? Because as long as we're on the same side of 40%, every forecast is going to do the same, right? You'll make the exact same decisions, whether you're 40% sure of rain or 41% sure of rain or 99% sure of rain. It doesn't matter. Your payoff is unchanged. Is that clear to everyone? So we now just want to make this a little easier to work with, so we make a few changes, right? So we're wanting to minimize expected loss instead of maximize expected utility, so we just put minus signs up. And then the second thing we do is we're going to normalize the problem. So at each world, or each, add and do like that, the loss of the better action is 0, right? So like when it rained, she was going to lose $1 no matter what. But that's not something she can control. So we can just, normalize by adding $1 to that column. And then we'll divide out the sum of, divide out the possible losses. So if you do that, here's the equivalent problem. And notice how perspicuous 2/5 is here. All right, so her probability here, the kind of cutoff probability, we now just see right here in this payoff matrix. Okay, when it rains, the better thing is to bring an umbrella, so she gets 0. If it doesn't rain, the better thing is no umbrella. We normalized, and this is how you would write the payoffs. All right. So if you wanted the earlier one, oops. Here, right, to add 1, then it's what, 0 and 5, minus 2 and 0. You'll see, then divide by normalize by the amount, and you end up here. So, oops. The sum of possible losses, okay. So right, so as I was saying was, you can really see here, right? I mean, all that's going to matter if she were to say, let's say someone said, well, before you decide, I'm going to give you a pill. Well, this is like the only problem we're imagining she'll face. She knows she's about to decide whether to bring rain. I'll give you a pill to make you, let's say she has credence 53% in rain. I'll give you a pill to make your credence 1 in rain, 0 in no rain. To kind of mess with your head, hit you with a rock over the head, something like that. And I'll give you, 2 cents. If you do that, she might as well do that, right? I mean, if all she cares about is her payoffs, she'd get that free 2 cents, and she'd end up making the same decision about the umbrella. All right. So the expected loss she gets of a credence in X is going to be very weakly. I mean, it's going to be a step function, right? Increasing with expected accuracy. So you think, what's her scoring rule? Well, all that matters is when her, she'll get 0 loss when her credence is on the wrong side of 40%. Right, so in the world where it does rain, she'll get, we're gonna say for now, we're gonna forget about the, when we normalize it, we're just gonna take that. She'll get the score of a loss of 3/5, really times 5, when she's on the wrong side of 0.5. Sorry, 0.4. And nothing otherwise. And when her score is 0, oh, sorry, when it doesn't rain, she won't lose anything when it's on the right side of 2/5, when it's below 2/5, but she'll lose 2/5 by taking the umbrella when it didn't rain. Right. So if you were to say evaluate, what's the expected value of my credence right now? Like, what's the expected loss of my forecast? Then whatever it is, right, she would assign herself using this scoring rule, the expected loss would just be that. Right, that's how bad by her own lights the things, you know, the beliefs, the stuff in her head is. Right? Is that clear? Because this is kind of the basis of the whole approach. This is kind of all it is that we're going to see a scoring rule is by this Servish construction.
You're just going to guess G0 if it does rain, G1 if it doesn't.
So I was thinking G1 is that it does rain. So when she's under 40% and it does rain, she'll incur a loss of 3/5. When it doesn't rain, but she's above 40%, she'll incur a loss of 2/5. I mean, then times 5, but we're going to forget about that for right now. Because the original stakes were higher. But. All right, and so, you know, this is going to be merely proper. You're going to evaluate anything on the same side of 2/5, or she'll evaluate anything on the same side as 2/5, the same. She'll think that gets equal expected losses or own credences. She'll assign anything on the other side a strictly worse loss. Good so far? All right. So let's just kind of, I mean, it's the same thing. We're just going to abstract from this a bit. I'm going to, I think, use Servish's same notation almost. You have a forecast. You have some decision that turns on your belief in X, in a proposition, in an event X. We've normalized, right, so that the right decision gets 0 loss, when X is true, and 0 loss when X is false. So there's the thing you want to do when X is true, and the thing you want to do when X is false. We'll call the thing you want to do D1, the thing you don't want to do when X is true, and the thing you want to do when X is false D0. And then there's going to be this cutoff point Q between 0 and 1. Right. Like 2/5 was Q before. And when you're, well, like what's the loss? Well, you don't get any loss when you do D1 and X is true. But when you do D1 and X is false, you're going to lose Q times some common factor W. I think W is the stakes of the decision. So that was that 5 that we ignored when we divided everything by 5. Right, the 2/5. And for D0, if you do D0 when X is false, you don't lose anything. When you do it when it's true, when X is true, you lose 1 minus Q. So the idea is for these Q problems, right, for a given Q problem, all that matters is which side of Q your forecast is on. W doesn't, really matter at this point. Still good? All right. Yes.
I didn't understand why changing expected utility maximizer to minimizer, change the expected loss minimizer, change it.
Oh, it's just slightly more convenient to do it with expected losses, and you get everything positive, and get 0 when it's the right decision. It's like, it just make it a little, you don't have to do it. It's certainly not mandatory. It's just gonna be totally for a minor convenience with the technicalities. Yeah.
Why would you not,
Sorry.
why would you?
Oh, well, because if you know what your decision problem you're facing, and we ignore by the sum of the loss, we divide out by the sum of the loss, it tells you. It won't affect anything, right? It's like if you know, she was going to lose $2,000 when if it didn't rain and she brought an umbrella, and $3,000 if it did rain and she didn't bring an umbrella. That wouldn't matter, right? Like she would still make the same decision as she would when it was the numbers I gave. So W just kind of normalizes that. For what, you know, it'll come into play later. But in terms of a single one-off decision like that, you know, multiply all the payoffs by 1,000, the cutoff point for your decision making will be the same.
Can you go back one slide? Previously, the lowest square root was 2 arguments, the first argument is not the subscript.
Oh, sorry, yeah, I moved it into the, again, probably should have done, but yeah, I'm just saying, yeah, I really, if you want, you can just have it as GX1, I guess is how I think I forgot to make that all consistent, yeah. So basically, right, you take a given problem like that, there's gonna be some cutoff point Q, we're gonna call that a Q problem. And the more general, you know, this is gonna be fairly general, not fully general, but you know, you can reduce a lot of compound gambles or whatever. You know, you can't quite do that with every forecaster if you have a finite event space, but it's pretty general to just kind of reduce it to these two. A 2-decision problem, right? Where it's when you're betting on a given event, and the forecast will look like this. Right, the square rule will look like this for a given Q problem. You'll lose 1 minus Q, 1 minus your credence. Yeah, 1 minus Q when your credence is below the cutoff point, and the event turned out to be true. And you'll lose Q when your credence is above the cutoff point, and the event turned out to be false, right? And you won't lose anything when your forecast is on the right side of Q. Right. So it looks like, so you know, this 1 minus Q and Q will come later, and you'll see kind of why that is. All right, so here's the whole move, right? Basically, everything is just gonna be this. When I you know, start my day and I have my beliefs in my belief box or whatever, I open them up, and I don't yet know what decisions I'm gonna make. Right. Like it could be that you know, I have a certain forecast for rain that I come into the day with. It's likely that one bet I'll make on this is whether to bring an umbrella. But you know, maybe as I'm walking to campus, someone will come along and be like, hey, do you want to buy a bet off me on rain for $10,000? You know, that pays out $100,000 if it rains. You know, that might happen. I don't know. A lot of things could happen, right? If I want to, like, say, you know, go to it turns on a flight right there. I mean, I have some idea about what bets I'll face. But there are a lot, you know, I don't know all the decisions I'll have to make for the rest of the day, or even the next few moments. And what I do when the world hits me with the decision I have to make is I'll look at my preferences, which we're keeping fixed, and I'll look at my beliefs, and I'll use those to make a decision, right? So I have some uncertainty over what those decisions will be. Could be anything, and I expect to like lose a certain amount based on my, what's in my head, right? Because since I'm not 1 and 0 on everything, I expect there to be some chance that I'll get things wrong. I'll do D1 when it turned out the thing was false, or D0 when the thing was true. All right, so W is now going to come back into play. You can break this down in more steps. So basically, that's all that'll happen to get you proper scoring. Strictly, we have nearly proper rules already. But there are going to be 2 factors that then are going to matter for how much I expect to lose given my forecast and rain, right? There's the density over Q, right? So I face the world ends up hitting me with a problem based on rain, whether it rains, like where my decision will turn on how likely I think it is that it'll rain. And I have some probability forecast for how likely it is. I have some sort of density, probability density, or maybe you think you want to have it in finite ways, then just probability assignment over how likely it is that the cutoff is going to be at 0.1, 0.2, 0.3, 0.4, right? So like if it's to bring an umbrella, maybe the cutoff is going to be 40%. If the bet is, if it turns out that someone just walks up to me and offers me a bet on rain at the odds, of 4 to 1, I'll have a different cutoff, right? My Q problem would be 80.8. So I don't know what Q is going to be. I mean, I don't even know if I'll face a Q problem on it, but I have some like beliefs about how likely a given Q is. But that's not all that's going to matter, right? Because when the bet, 1 Q problem, my cutoff might be 0.4 or for bringing an umbrella. If that's the Q problem, it's very likely, but it's still, if I get caught in the rain, it's not the end of the world. If someone comes and offers me a bet at 4 to 1 odds on rain, but the stakes of the bet are, $1 million that I could win, and then that's a much more important in terms of when I think about my expected losses. That making the right call on whether to take that bet matters a lot more. So it's not just how likely a given Q cutoff is, but how likely, how important that W that we talked about earlier, the stakes of the bet at a given Q point, the expected value of the stakes for a given cutoff will be. Right, so kind of just to make this concrete, I'm right now, let's say I know I'm going to pay some bet on rain. I'm either going to face Q1 or Q2. If the world hits me with Q1, I have a cutoff of 0.5. If the world hits me with Q2, I have a cutoff of a third. But it's 15 times bigger in terms of importance. Right, so like if I think what's my expected loss, well, I have to think, well, what's the probability I'll face Q1? How important is it for me to be on the right side of 0.5 if I do face Q1? And then how likely is it, plus, when I weighted by my expected value, how important it would be if I face Q2 and my cutoff being on the right side, my probability being on the right side of a third. All right, we good so far? Yeah.
Using 15 and multiplying it by 15, that reflects how much worse would be in the moment rather than how much better it would be right. Is that right?
Well, I mean, you could look at it either way.
But
right, yeah.
Right is you get 0. So
yeah. So it'd be, 15, it would be, I guess, 5 or 10 better to make the right decision than the wrong one. Right? I mean, you can pick either one as the status quo.
But
Yeah.
comparing Q1 and Q2, if you make the right decision in both, there's no reflection that that was great, that was like more important in Q2 than Q1.
Yeah, I mean, your final payoff would be the same, right? But if you say we're between, you know, if you had credence 0.4 and X, I mean, right, these both turn on X, you know, credence 0.4 and X, you know, then I'd make potentially the right decision in one versus the wrong decision in the other. You know, how much that would matter doesn't like, yeah, it won't affect, I mean, right, then there's a big difference, right? So everyone's with me so far? Yeah, I mean, we're basically towards right at the last step, except we have to go infinite here, right? Make it continuous. So like, let's say, you know, let's take the finite case once more, just generalize, and then we just have the very last step. If you had, say, finitely many potential Q values, right? You knew it was going to be, the cutoff was going to be 0.1, 0.2, 0.3, 0.4, 0.5, something like that. What would you do? Well, I would expect that for any Q problem, if I was on the wrong side and it turned out true, I would lose 1 minus Q for that Q value times, well, you could then sum over the weights if you wanted, but you can just say the expected value of the stakes, I would, you know, given that I'm at that Q cutoff point. And then, you know, I'm just going to discount that by how, like, sorry, kind of abbreviated the notation, how likely it is I think it is that I'll face a cutoff point of Q. Right, so sorry, if you had, say, the Q value is drawn from some finite set, let's say fancy Q, that should be the probability that fancy Q is. All right, so I guess you can, yes.
Sorry, I don't understand the way it is the strain of loss, and I don't understand that for what it is.
Yeah, so, oh, sorry, so, yeah, how bad the expected, or how big the stakes are, right? So at a given that I'm facing a Q problem. So imagine, take the rain example. Well, let's say the Q probabilities go to betting instead of umbrellas. It's kind of hard to figure out. Oh, sorry, W is a random variable for how big the stakes of the bet I actually face are. Right, so W here would be, sorry, that should have been clear. Let me just go back to here, right? So in Q1, W would be 1. And in Q2, W would be 15. Right, but like I could also face Q2 prime, where the cutoff was 1/3. Like say, you know, given that I face a cutoff of 1/3, a Q equals 1/3, you know, I'm still unsure what how important the bet is, right? Like I could face a bet where the stakes are 1, where the stakes are 2, where the stakes are 15.
You use the same threshold for both bets?
I would use the same cutoff. So if I had Q2 prime, right? So like Q2 prime. So let's say you tell me, Ben, you know, you are going to face this bet on X and X bar with no 15, right? Or you say, no, you're not going to face it. You say you're either going to face this bet with this payoff matrix or loss matrix, or you're going to face that one. Right. Given that happened, like I was going to face, like you told me that, you know, all that would matter for what I did. It wouldn't really matter. 15 wouldn't matter, right? I would still just do the top thing if my credence was above 1/3.
Yeah, it's because Q2 and Q2 prime are about the rain and Q1 is about some race somewhere. So they have.
Oh, no, they're about the same thing, because they're both turning on X. Right, so like I come into the day, I'm, let's say, 40% confident that it'll rain or whatever. Well, one decision is, there's a bet that costs 50 cents that will return $1 if it rains. Right. Well, that could happen to me. So I might be mixing things up with the signs, but another thing that could happen to me is there's a bet that costs 80 cents or something, or 50. It costs 55 or 50. Sorry, instead of 80 cents, it costs $55. That returns $100 if it rains. That's another thing that happens. There's another bet that happens where it costs 55 cents and returns $1 if it rains and $0 if it doesn't rain. There's another,
So we have one random variable. We don't know which bets we will have, and each bet has a different.
Yeah, so we don't. So right, we have one random, or let's say binary variable. Right? Yeah, it's gonna be it's be true or false. I don't know. There are two things I don't know about my decision. That is the decision I'll end up making. The world's going to draw some decision, throw some decision I can make. Where what matters for any of these decisions is whether X or not X. All right. And there are two things that I'm uncertain about, right? What the loss, I'm uncertain what the loss matrix will be, but there are two things that matter about the loss matrix. How big the stakes are going to be, and what the cutoff point is for whether I'll do one thing or another. Take the bet or reject the bet. So right. So even once you fix, you say, well, you told me the cutoff point is going to be 1/3. I still have further uncertainty that I'm taking into account of as how, what I expect, how important I expect this bet to be. Right. And so that won't matter if I knew already it was just 1/3. But if I say, hey, I don't know what's going to happen to me today. But I could face a cutoff point of 1/2. I could face a cutoff point of 1/3. Don't know if the stakes will be either way, but I expect if the cutoff point turns out to be 1/3, the bet will matter a lot. Like how my day goes is really would be affected a lot more. Does that make sense? So that's where the expected value of the stakes given a certain cutoff point. We're going to talk about this more. I guess later on when we think about how to apply it, right? So like, like in an insurance context, the cutoff point, if I'm going to buy insurance, the stakes could be really high, but kind of my credences will be pretty extreme, likely to face cutoff points that are important, near 0 or 1 for my forecast. The Q values there. If it's rain, I probably don't expect a lot of like either super important high stakes bets, and it would be weird if there was something I was only going to do if I was 99% sure of rain, but not 98% sure. Right? Like that doesn't usually happen. I mean, it could happen, but it'd be weird. It's like if I'm 95% sure of rain, I'm not going to do this. If I'm 98% sure of rain, I will do this. It's like I don't know, unless you're offered actual bets in Vegas or something on weather. It's not the kind of thing you would expect to face, but you could face on rain. Is that intuitively helpful? Right, so that's just kind of these three factors, right? It's I only lose when I'm on the wrong side of the cutoff, and how much I lose is going to be the W value times the Q stuff. So how likely is it that I face that a cutoff point of Q times how important, what would my loss be, being on the wrong side, and how important would I expect that the bets at a given Q value B. Yeah.
Okay, the W depends on the bets, not on the threshold.
The actual value of the bet of W depends on the true what the bet is. Yeah. So the idea being like with Q2 prime, like once if you fix the cutoff of a third, right? If I say conditional on it being a third as the cutoff point, Q equals 1/3, I still have the uncertainty about whether I'll be facing Q2 prime where the stakes are just 1, W is 1, or if I'm facing Q2 where the stakes are 15.
And also the difference between W and Q.
Right, because the idea was, because that's, even once I know the cutoff point is a third, I could face either Q2 prime or Q2. Right, I could face a big bet, an important bet, or I could face an unimportant bet. Whereas say, in this tour example, if I knew the cutoff point was a half, I knew the stakes were just 1, right? So I say, I was 50% sure I was gonna have the cutoff point of a half, 50% sure I was gonna have a cutoff point of 1/3, but given that it's 1/3, I would, I have, say, 50% chance of low stakes, 50% chance of high stakes.
But where is the probability of going to prime?
Oh, well, that's I'm just kind of doing as the, you could unpack EW, the expected value of W given Q. So the expected, that would be times the probability W equals, so for this one, I could have it say, for instead of EWQ, I could have the, fixed Q at 2/3, right? I could have in there some internal summation about the probability, W equals 15, given Q equals, or what I have, 1/3, times 15 times, plus, if you want to unpack that further. Is that, okay, all right. Right, and so you see the balance, so a couple things here, we see there's 1 minus Q for every Q, and Q for the G0 value. And then we also, right, it's only, for X, we're only summing over our potential Q values. So, right, it's only when my credence is low, below Q, that I'm going to lose anything for X. So that's like, look at those bounds of the summation. Right, it's like when my credence is below the cutoff, and it turns out true, that's when I have a bad day. When my credence is above Q, and the thing turns out false, that's when I have a bad day. That's the only time. Right? Okay. So we're basically there. Oops. Right, so you think of the EW given Q, the expected importance given of having a credence on the right side of Q, like all that stuff, right? So I'm going to do one slight simplification first. This is kind of how I think about it, not being like an analyst. When we go to the continuous case, right, you think there's some mass around Q, right? The expected importance at a Q point is going to be this thing you can think of M of Q, which is going to take into 2 factors, right? There's how likely it is to begin with that the cutoff is Q, or in this small region around Q. That the cutoff, the actual problem I face will be some small region around Q, and then given that it's there, how important do I think that it is that I get on the right side, right? Those are the 2 things. It would be really important if I have this problem on rain where my cutoff is 99.99, like that'd be, let's say, maybe really important. I can't even, it's hard to imagine a real decision other than just literally a bet offered to me on rain. But it's also super unlikely, right? So like having my credence and rain on the right side of 0.99 doesn't really seem maybe all that big of a deal. Okay, so what would happen then? Well, you know, you can think of it, this is gonna be the slightly very simplified version of Servish's theorem. This is the one I kind of, you know, would basically think of. This is basically all the scoring rules you might care about. That's to, you know, make it so you can integrate and everything. But, right, what am I doing? Well, I just replace the sums with this mass function m of q, kind of codifying how important it is at this q point. And then I integrate, right? So what do I integrate? Well, I lose 1 minus q times the expected importance of q when it's actually true. Right, and so you can think of G1 here as saying, how, given that X actually, you know, turned out to be true, if X did turn out to be true, right, you still don't know what bet you faced. Yeah, let's just say I told you, suppose it turned out to be true, how much would you expect to lose there? Right, and I have to kind of integrate, well, it's only where the Q is above my credence, the cutoff is above my credence of X. So that's why I'm integrating from X to 1. I don't know which bet it would be, right? There's 1 minus Q for the Q times the expected value of the importance. Yeah. So that's how much I would expect to lose if it turned out false, or turned out true. And then, you know, similarly for G0. So is the like intuition now clear? Like, I mean, is this? Okay. Right. So when is it going to be strictly proper, right? So we saw for all the in the finite case when we did this, it was always merely proper, right? I mean, it was like if we're in the same cell, it's going to turn out merely proper, right? It doesn't, you know. Well, it's going to all that matters. Basically, MQ isn't going to be 0, right? I assign some chance of facing any Q problem. You know, you can make exceptions for measure 0, as long as you can keep integrability. But as long as, you know, I kind of could face a bet at any Q cutoff point, I get strict propriety. Sorry?
Can you explain this part again?
The strict propriety part? Yeah, so the idea was, right, it's like, so I had to go back to the finite case. I mean, there are a few ways of seeing it. I'll ask you to kind of do the exercise to prove it in a minute, but I think more intuitively than the way you might prove it here is, so right, so remember I just gave Q1, let's say I only could face 2 Q problems. I faced Q1 where I had a cutoff point of a half, or Q2 where I had a cutoff point of a third. And well, if you wanted 15 or not, doesn't matter right now, right? So we kind of saw when we just did the single case, where it was real, well, first let's say we just had Q2 or something, right? All that would matter, like if I had a credence of 0.2, I would expect to do just as well. You know, I would lose in the exact same situations where I'd lose as if I had a credence of 0.1, right? So we kind of saw that with the initial example where we're sure just about the umbrella, right? And if I had a credence of 0.4, I would expect to lose just as much as if I had a credence of 0.9. All right, well, when I could face either Q1 or Q2, right? If I have a credence, say, 0, 1/3, 1/2, right? If I have a credence here, right, that's gonna, I'm gonna evaluate a credence there between 0 and 1/3, you know, if that is 0.1, 0.2 or something, I would expect that to do just as well, because in both problems, I would make the exact same decision, right? And if I were here, I would, you know, so as long as I'm kind of always in the same cell, I would expect to do just as well, right? So now, like, let's just add more possibilities, right? So if I had a potential Q problem here of where Q is 0.15 or something, well, now I wouldn't evaluate that just as well. Right? So if M of Q is 0, I say assign 0 chance over a certain region of facing a Q problem. Then I'll end up with a merely proper rule where say like 0.1 would assign 0.2 the same value. Because I was like, well, there's no way I would face any Q problems that turned on this. But, you know, as soon as I start adding the continuous case, there's going to be some chance of a Q problem where I would make a different decision when I had a credence of 0.2 versus 0.1, right? So if it's always positive, then take any 2 points, there's some chance of making a different call, like facing a decision where I make a different call. Basically, I mean, you'd always just think, right, there's some way, if I had a credence of 0.1 versus 0.10001, someone offers me a bet on the proposition right between there, we're going to make, there's the decision boundary will change. So that's kind of the intuition. Yeah.
Being in the same set, or you mean being in the same row?
Oh, sorry, I meant like the cells here, I think were kind of all the credences between 0 and 1/3 with one cell, all the credences between 1/3 and 2/3, all the credences above 2/3. That, you know, those credences will all make exactly the same decisions. I mean, in the original case where you could face the Q problem, you knew you were going to face one of 2 Q problems. One either with a credence cutoff of 1/3 or credence with a cutoff of a half. If you're kind of always here, yeah. Yes.
Just so when the Q is 1/3, so if the thing is the value of my subjective probability when it's below will not change my choice. So for one event will not change my loss. But if there is a repetition, my expected loss will not. How I compute my subjective loss will not be the same.
Like if I keep having to make the bet over and over.
Yeah.
Yeah, as long as I mean the stakes in some sense you could go up, right? Because like
my expected loss will not be the same if the Q is 0.1 or 0.2.
oh, my expected loss would change. Yeah, but my what bets I took or did not take.
Yes.
Right, would not change. So I evaluate everyone who's close enough to agreeing with me that we're on the same sides here, of 1/3 and a half. I'm going to be like, you're going to do just as well or poorly as I did, you know. And if you paid me $1 to change my beliefs, at that point, you know, I'd take, you know, to give me a pill to do that, I would be wise to take it. Right? That's a. So for the aficionados, right? Like here's the full form, and you see now we get the if and only if. So you can think any scoring rule you really care about, you can kind of do this way. Obviously, you can add constants in the beginning, you know, because you think, well, I mean, right, just kind of intuitively, if these are nice enough that we can take derivatives, blah, 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 right, those are going to zero out. Everyone's getting the same thing there. And instead of M of Q dq, we just go to a measure.
So what's the statement there? J is
Oh, it just this is right at the 0, 0 and 1 points, right? That sorry, that should be G of T, GI of T. Sorry, yeah, I have a new one. That's the exactly right. Yeah, sorry, that should be GI of J equals the limit as T goes to J for J being 1 or 0 of G of T, just so weird stuff doesn't happen. Teddy can tell you all sorts of stuff on the infinite stuff. Other people can, you know, talk to you about, you know, this is Lebesgue integrals, so there are always nuances there. I don't know. It's been a long time since I had analysis.
You have GI.
What?
G sub I.
on the board, just on the.
Did I write this wrong?
No, you just read the subscript.
Okay. Am I good now? Right, so, but, I mean, basically when you're working with it, you might as well think about it this way and realize you can kind of get anything you want. So, right, so you want to make a scoring rule that's strictly proper. Pick M of Q, or pick mu, if you're a fancy person. I'm not, and get, I guess I'm kind of doing the same thing effectively. In my head, I always read it kind of this way. And make the scoring rule how you want, right? Where you're kind of thinking, where am I getting mu from? What am I getting M of Q from? Well, in this region of the unit interval, how important, take a small region within there, how important is this region? This tiny region, how important, kind of around 0.5, let's say 0.499 to 0.501, how likely do I think I place bets in that region relative to other regions? How important do I think those bets are going to be? Sorry, I trouble with this mouse. So you think each GI will measure the expected loss of that forecast, giving X's truth value is I, right? So even once you learn the forecast or the truth value of X, you're still unsure what bet you were facing. You don't know how bad your loss would be. The expected value conditional on X being true is going to be G1. And if conditional on being false would be G0. Okay. Maybe just to get a little more intuition here. So this is an old graph. I was supposed to make a nicer version. Sorry. Okay. But you can see here's the Breyer score, right, for 1 and 0, the score and the log scores. Here would be the M of Q. So for Breyer, right, you're just thinking it's just 2, right? It's just constant. We make any constant if you want to scale. So you're thinking kind of no Q value, maybe each Q value is equally likely, none's more important than any other. Everybody's equal. For the log support, what is it? Well, what really matters are these kind of low probability things that would turn on like exact, low probability or not, high probability or not, or very high, kind of more and more, right? So it's stuff towards the end that I really care about. Odds of 100 to 1 are much different. For the Breyer, odds of 100 to 1 are not much different from odds of 1,000 to 1. Right? For the log, they're very different. Because that's odds talk, I guess, is a lot more natural. And then I think for spherical, what does this look like to me? I mean, I don't see spherical come up too much, aside from just as an example of a scoring rule, but it looks like binary classification, right? Like kind of basically what I expect to be doing is asked to classify it as true or false, right? So it's kind of, if I'm on the right side of 0.5, is really what matters for spherical. Yeah, I expect to face a bet that turns on, I have some probability, and I expect to face a bet where I have to say guess yes or no with a cutoff, equally important or something like that. So just being on the right side of 0.5. So I think, you see the graphs of the scoring rule, I mean, maybe you could kind of look at it and stare and think about derivatives, but I think kind of looking at it on the support function, what's your support function and generating your scoring rule that way is the better way to go. Maybe I'll leave this as a home exercise. If you want, I mean, one thing that I thought was kind of cool about this, right, is so the absolute value score, you can kind of see why it wouldn't work out. Whereas just taking the absolute value, there's not going to be any measure that will get you the absolute value. Right. But if you want it to be kind of absolute value on one side, you can do that. Right, so you say when X is false, I want the absolute value score. Or when X is true, I want the absolute value score. You can have both. Easy exercise, we won't take any time for. But convince yourself you can construct that by picking an appropriate mu, right? So I found personally, like when I want to prove something about scoring rules, like people will be like, can you get an accuracy measure that does this or not, whatever. I found the Shervish method to be the most, I mean, it's often kind of tedious. You have to like fiddle around with a mu, you have to, you know, but like you can often prove a theorem by just looking at the bounds of integration or something, you know, and comparing things based on the bounds of the integral you would generate, picking the right mu. I found that personally, if you do anything with scoring rules, easier than any of the other methods that are, you know, I think often harder to deal with. So say about like 2 minutes. Okay. All right. So I think, right, you can kind of more fine-tune things this way. You can kind of maybe look at some of these examples. Let me see if there's yeah. You know what? It's the last day. Let's just cut it off here. There are lots of applications. I was very worried that I was going to like be done in like 70 minutes because it's an hour 45 is not like a usual amount of time to take. So I think there are a lot of applications. I think this generalized loss approach that Shervish came up with is both really nice conceptually. It avoids some of the, if you're in the philosophical literature and you're not, you know, you're kind of a free agent, you don't care so much about this, you know, making sure it's purely alethic or something. I think it gives a really nice picture of what proper scores, strictly proper scores are, you know, why they work, what's special about them relative to improper scores. Yeah, I think also if you want to do any of your own, you know, I'm not like the world's best theorem prover, but whenever I, you know, want to prove a theorem about scoring rules, I just like use the Shervish representation as my first approach and try to prove it using that. It often turns out, you know, a little bit tricky calculus, but nothing really harder than that. And then, you know, if that fails, then I just give up. But other, you know, you might try something else instead, if you're smarter than I am. So I guess maybe I'll leave it there. Thank you.